Welcome to the Decode Podcast with Elias Malfovan, Daniel Stanfill, and Sean Kincaid.
Welcome. We are joined today by Mr. Chris Hunrath. He is the Vice President of Technology at Inselectro, hails from San Jose, California, the great state of California. He is an IPC certified interconnect designer with 40 plus years of experience in our industry. So thank you so much for joining us, Chris. Obviously, my counterparts, Mr. Sean Kincaid and Daniel Stanfill, also join us. We appreciate the opportunity to speak with someone who's probably kind of seen it all, especially in terms of laminates and substrates and all things that Sean loves to talk about, circuit boards. So welcome.
Yeah, thanks for having me. I started in this business doing electroless copper for multi-wire. I don't know if you guys know what multi-wire is, but it was literally 4 mil diameter magnet wire with a polyimide coating, and we'd ultrasonically melt that into an adhesive. And then we'd take those layers, laminate them together, and one of our hallmarks was we could do 22 layers of density in one layer of 4 mil wire.
So is that where the term PWB comes from?
Actually, not really. They used to call it discrete wiring. There was actually an IPC spec for it. The problem was it was way ahead of its time. We're talking, early 80s. We were doing that kind of density, and very few people, just the high-end, really, really high-end cutting-edge computing people that would use that technology. Some mil-aero stuff, but it was slow. I mean, it would take hours to wire one layer. It looked like a drill machine with those wiring heads on it, but it just took a long time to wire that layer where you can print and etch 22 layers. Well, really it would be, 11 cores, right? You can do those very quickly in print and etch. So it just couldn't keep up with the speed of manufacturing. And like a lot of technologies, the immature embedded technology, no pun intended, tends to win out, even if it's not the best technology. So, and that we see that in processors and other types of devices. So,
Elias, on that on the SMTA's website, that Six Sigma thing I did recently, Dr. Ron Lasky was talking about the printed wiring board is still what you should call a raw board until it has components put on it. It's actually just a PWB, not a PCB.
Okay.
Oh, well, see, you learn something new every day.
Yeah. I don't know if we need to get caught up in definitions, but
definitely not.
Yeah. So, I've been in the business a long time. I noticed in our industry, one of the things I did want to talk about today, so thank you again for having me on, is there's a big age gap. There are people my age, maybe a little bit older, maybe a little bit younger, and then we have some great young folks that joined our company in the last 2.5 years, which is great. But there's this big gap in the middle, and one of the things that we want to do is transfer our knowledge to the next generation. And so we're trying to encourage young people to get into the business, whether it's at our company or one of our suppliers or one of our customers. So that's very important to us. We're trying to do things to try and encourage that kind of participation. I think it's a great place for a young person to carve out a career. You're not going to be easily replaced by AOI. Sorry, not AOI, AI.
Sure.
I've spent too many times in the interlayer department at a PCB shop to say AOI. But AI, I had this conversation just this week where I was helping a customer with a stack up. They were trying to decide, how to do all the layers and what's the lowest risk, because they were trying to do some heavyweight copper, but they were trying to keep everything within a certain thickness tolerance. So, we're making judgment calls. We have calculators, right? And AI.
Trying to find that balance, right?
Right. Find that balance. And that's not going to be easily replaced, that kind of talent. Another thing I had, recently was a customer of mine calls me up and says, hey, the cert for the material doesn't match, what's on the print. And the source inspector is ready to reject the whole lot. These were polyimide boards, very expensive boards. And it turned out what happened was a younger designer, cut and pasted from an older print, and he separated the letters or actually combine the letters GI and in, as in the word in. So this guy was looking for a GIN material, and it was really a GI material. And anyway, we were able to sort it out because you can see on the print actually where these things were cut and pasted. You actually see like a little space, and you can see it made more sense in the sentence. Anyway, to make a long story short, we want to make sure young people coming into the business have the knowledge to be able to put the right material type on the print. Another example, recently, a customer's customer put a particular material type in and asked if that material contained FR4. And AI said, no, it does not contain FR4. And it was really how you asked the question. What he should have asked is this material an FR4 grade? And if you ask that question to AI would say, yes, it is an FR4 grade. It's a flame retardant epoxy with fiberglass reinforcement, meant for circuit boards. So again, this is the human part. This is the knowledge we want to transfer to the next generation.
I don't think these guys truly understand how far like laminate has advanced, even like in the last 20 years, right? Like, because when you think about it, right, it's just foil, right? Some woven fiberglass foil, right? Like, it's nothing too crazy about it. But and I don't know if this has ever happened at your company, but some of the suppliers I was using in the past, they would have this issue. Like when I started, we used to, I'll tell you what was replaced in every PCB fab. We all used to have shearing guys, right? And we used to get these huge 36 by 48, I think, inch sheets of copper.
That's a standard sheet, a standard laminate sheet.
And then we'd have to cut them up, right? My dad was crazy. He liked to do 12 by 12 panel and 12 by 14 all the way up to 12 by 24. And then he'd go all the way around, right? So you go 1824, 1624, just in like every combination. And it was a nightmare for me in plating and every other tooling everything in there. But he's like, oh, I'm saving so much copper by not having 4 inches on it. And in theory, he's correct on that, right? But the rest of the process is really...
Especially if you can just make your kid do all of it.
Yeah, yeah. But like, when I started, I remember it was common practice to bake the FR4 when it came in. Like we had to bake it for a couple hours before we actually used it. And I know this isn't commonplace, but and I know it's not good, but it was really cool to see. So sometimes after you etch the copper off the board, there would actually be bugs that were laminated inside the laminate, right? So you would actually see like little mosquitoes or different types of flies in the actual thing. And you go to expose it, you'd be like, what's that on the panel? And then you look and you're like, hey, it's a bug. And like the whole shop would come by, right? And be like, look at this, and I from what I hear, I haven't bought any in a while, but those type of issues have been taken care of. But like, when you go from that type of process to now they just get these sheets shipped in 18 by 24 lot coated and everything's in there, right? And it's all traceable now, and you guys know everything. And if there's a problem, there's like a recall and stuff like that. So it's just totally different than and the type of different materials out there. When I started, I think like TG 130 was like it, you know what I'm saying? And then lead free became a thing. Like we didn't even have a lead free pot for a while. And then once we got a lead-free Hazelpod, then everybody wanted TG 170, and I did too after because you can get away with more dips, right, on a 170 than you can with a 130. It's your laminate will like start to crack, it does not like that. So like now when I see a customer, they request like FR4 TG 130, and it's a lead-free board, I'm like, dude, just spend a little extra money here. It's not that much money. But Chris, I just heard something recently from my buddy Dennis. He runs a PCB shop over in Chicago, Circuit Engineering. And he was trying to explain to me the difference between TD and TG. And he said a lot of people focus on the TG, but you should really focus on the TD. Can you explain on that a little bit? Because it was kind of like, and I just heard about this literally a couple of days ago, and it was just extremely eye-opening to me that here's this thing, and he says, like, North America focuses way too much on TG. Like, TD is what we should.
So I actually have a PowerPoint slide deck on thermal analysis of PCBs, and it's like I said, it's very agnostic. It pulls up the IPC specs, pulls up some definitions in material science, basically in thermal analysis, and it explains everything. Anyway, so TG is glass transition temperature. It's when a material changes from its glassy state to an amorphous, somewhat plastic state. Usually used for thermoset resin systems, but it can apply to many different materials, even metals. But it's usually reserved for thermoset. Plastics are in that two broad category: thermoset, thermoplastics. We do use some thermoplastics in the PCB industry, but to be solderable, they have to have very high melting points, right? So you can do assembly on them, right? Reflow assembly. So the glass transition temperature is important because usually those materials undergo a change in CTE. Below the CTE, their expansion might be, in the z-axis, might be 50 parts per million. Above the TCG, it's 250. So the higher the TG, the later on that rapid expansion occurs, the total expansion is less, and you get better results. And so when we saw you talk about some of the old resin systems, right? When multifunctional systems came out and we bumped the TG from 125 to 180, or even 170, you had much less z-axis expansion. That's the simplest way I can put it, and that's not all that simple. The glass, or the decomposition temperature, or TD, is when the polymer starts breaking down, and you measure that by weight loss. And the IPC test isn't the greatest, only because after something's undergone 5% weight loss, the material's damaged, right? The polymer is damaged. It's starting to break apart. You're turning some of the components, the chemical components, into gas. That's how we measure it, by weight loss, right? At that particular temperature. It's done in what they call a thermogravimetric analyzer. You heat up the sample and wait till basically you measure when you see a substantial weight loss, 5% weight loss. It's good in that it is a good way to compare different materials. So if I have a material that has a decomp rating, or TD rating, of 450, it's going to hold up much better in a continuous thermal environment than a material that's 340. Most lead-free phenolics, which is sort of the standard for FR4 now, phenolic cured epoxy, are in that 340 range. Whereas polyimides could be over 500 Celsius. They can be very, very high. So they're very good for continuous thermal operation. Epoxy polyimide blends are somewhere in the middle. They're not as good as pure polyimides, but they're much better than the phenolic epoxies. There's a whole other range. Sean, you talk about different laminates. We have polyphenol oxide. We have polyphenol and ether. So there's some old cyanate ester systems. I mean, when I started in this business, we had difunctional epoxy. It was G10 or FR4 if it had the flame retardant in it. And then we had polyimide, and that was it. We had some specialty materials for multi-wire, but now there are so many different resin systems and resin blends out there. It's just a whole sea of different products. And then you can add filler, and you can add, air-filled spheres for lower dielectric constant, and you can do all kinds of things. Sorry, I'm just going on a bit. So
no, this is great. This is great.
It's fantastic. Yeah. I got something I would like to ask you. So Daniel and I recently attended SMTA High Reliability Conference in Dallas, and Sean was not there. So that's the for the listening only audience, Sean is doing something akin to a 6-year-old who didn't get to go to the park.
How about this one too? How about that?
But two out of the three of us cared about high reliability.
So the conference was centered on cleaning and conformal coating, and Mike Conrad was giving a cleaning master class and was talking about electrochemical migration and sort of three of the species of ECM, and one of them was CAF, right, or conductive anodic filament. So I think it's having you on and having just sat in that class, that would be a topic that I'd be interested to hear kind of from your end of things. What are the considerations? How does that happen? How do we avoid it?
What is it in the process that actually allows for that condition?
Well, it's It's a little bit complicated because there's a material component and there's a manufacturing component, right? And when I say manufacturing, I'm not talking about making the laminate, because that I consider the laminate manufacturing part of the material. I'm talking about when the PCB fabricator gets the material. So
Yeah, sure.
for CAF to happen, you need a couple of things. You need water molecules, and actually, more specifically, hydrogen, and you need a pathway. And to make a CAF-resistant material, if you can reduce the water absorption and you can ensure there are no pathways, now you have a CAF-resistant material. Now, a board shop can ruin that with poor drilling. They can create fractures in the material that become pathways that you throw a filament in. But the material is important too. So, does the material have filler? Because the CAF filament can jump from filler particle to filler particle if the filler is not properly wetted and bonded to the resin. Same with the fiberglass if it's a glass reinforced material. So, there are film-based materials that are pretty immune to CAF. But if they have filler, that may not be the case. But with the glass fabric reinforced materials, certainly if you don't have good glass to resin bonds, that could be a pathway for CAF. I've even seen hollow filaments where a bubble gets incorporated into the glass fiber. I mean, think about the actual filament of glass has a bubble inside it, and that's a pathway for CAF. It's pretty rare, but it can happen. But if you have a pathway, you have moisture, the material can absorb moisture, and then you need DC voltage, and you literally break water down into oxygen and hydrogen, and then the hydrogen makes the copper in your circuitry mobile, and then it will literally electroplate itself or galvanically migrate itself through that pathway, and that's how you have CAF. And it can be very insidious because it can happen 2 years after the board's manufactured, and then all of a sudden you have a short, and it can. I've seen boards burn up. Now, fortunately, the flame retardants keep it from catching on fire, but it can do a significant amount of damage. Of course, the other component on the manufacturing side is how close are my plated through holes to my traces? How close are the traces? All those things are factors. And when we do CAF testing, we do them at different spacing between the vias. Tighter the vias, typically the less CAF resistance you have.
Sure.
Especially if you're doing it at high voltage. And we have some materials that we test at 1,000 volts that are used for electric vehicles. 1,000-volt CAF test. So yeah, I mean, those materials tend to be very good at high voltage applications. Kapton is very good at polyimide film, very good at resisting that. But that's more of a Z-axis barrier if you're incorporating that into a PCB. Of course, Parylene, conformal coatings can help because they tend to resist moisture, so they keep the moisture from getting into the PCB. So
Parylene?
Yeah, Parylene.
Is that an ultra thin coating, or
that's a conformal coating that's typically vapor deposited onto a PCB. Very hard to get rid of, though, if you need to do any kind of rework or
rework's almost impossible with that one, right? Like
if you have to remove a component, it's a challenge, but it is good for boards that might be in an environment where you'll see moisture.
A lot of boards that go up into space get Parylene coating.
Yeah, so on that subject, I don't know if you're familiar with atomic oxygen in low Earth orbit, but the atmosphere is very thin, and so you have oxygen and other atmospheric components, but at very low pressure, right? And now it's being energized or excited by the radiation from the sun, right? So you have these two things combined. What does that sound like, right? You've got low pressure atomic oxygen, and you've got energy, right? Sounds like a plasma machine, right? So it literally etches materials in space. So fluoropolymer materials tend to do very well. Parylene does pretty well. So that's why we put these things on the PCB to make them survive better in those environments.
Yeah, I mean, most people aren't aware of like how many tanks your PCB is going to go through, like during the manufacturing process, right? Like they have no clue how much water, right? And each tank is segregated, right? You could have, I can't even imagine like just trying to isolate because that's the problem when something goes wrong in PCB Fab, you have to play a detective, and
Mhm.
you know it hasn't happened at the processes that haven't happened since, but you to find all those, like when you're talking about that bubble that you found in there, right? Like I was thinking,
Yeah.
man, do you know how many steps he had to go through just to make sure that this was this or that, and it's nuts. And to think that it's
That's
tough.
not the first place you're going to look when you're troubleshooting. Was there a bubble in my glass filament?
And it's tough to have a clean
Right, yeah.
PCB shop. It really is. Like it's a dirty blue collar job, right? Like it is what it is, And
Electroless copper is 20 to 25% of the water usage in a board shop. It's a big
What I-
deal. And a modest board shop, just the electroless copper line will use 55,000 gallons a month, in their
Wow.
electroless copper. Yeah. So
And think
that's
about,
a
too,
small,
like-
that's a smallish shop.
we're
So-
blasting those boards with like pure sulfuric heated. You know what I'm saying? Like this is. So that's why I was like, when Mike was talking about this stuff sometimes about like it getting trapped in plating one time, I kind of went after him. It was the only time I ever like really went after him a little bit. It's like, well, I'm going to zap this thing with like pure sulfuric basically almost, or 10% at least before it goes in my plating tank, right? My plating tank has a ridiculous amount of sulfuric in it. So like this thing's constantly being cleaned, just constantly being cleaned and trying to strip residues and stuff from it. And
the board does go through a lot of processes. Yeah,
it gets
a
beat
lot
up.
of chemistry, chemical processes, a lot of baking process, high pressure, through the lamination process, but it seems to do okay, for the most part.
Yeah. And, I don't know. It's just weird because it's the preventative maintenance in PCB Fab was so important. Like you were talking about earlier about drilling, right? Like the vacuum bags on a drill can make or break your company. Like if you don't clean those things out and you get those little burrs in there, because you're talking about those little, nicks, and I know how those nicks get formed, right? And you're talking about like, old drill bits or, when we had the green Mylars back in the day, that stuff would whiz up on your bit a little bit, right? And sometimes get in the hole. It was just nasty. But there was one thing about plating that you mentioned that I wanted to talk to you about was pattern plate 2.0. I'm curious.
Oh, yeah. Yeah. So I just had this conversation with one of our largest customers today. They're being told by component manufacturers that the BGA pitch is going down. And that's not news, right? I mean, we've seen, 1 millimeter pitch, half millimeter or 0.5 millimeter pitch. They're going to go pitch, right. 0.3, 0.25, right? So one of the challenges, of course, we have in designing and making a PCB is routing, all those IOs in the bottom of BGA. I mean,
Sure.
the BGA really, the development of the BGA really exploded the number of layers we have in PCB. Because before that, when you just had connections on the perimeter of a chip package, you were limited to how many connections you have. Now we've got components with 2,000 IOs, right, or more, right? So, which has allowed more silicon and more components or transistors inside the package. That's why we have billions of transistors inside these BGA packages, these chip packages. Anyway, one of the challenges that we have is how do you route that, right? And fortunately, from a signal loss standpoint, if you neck the trace down for a short distance, right, and that distance is 1/4 of the rise time or less, it's not going to ruin your transmission line. It'll still work. So what that allows you to do now is make narrower
Like high speed applications and everything.
The applications, right?
Okay.
Yeah.
Okay.
So you can neck the trace down and not mess everything up, as long as that neck down is short, and that usually is within the framework of a BGA footprint, right? You can do that. You can neck those down. The challenge is a lot of fabricators don't like to go below 3 mil lines, so 3 mil features, and it's for good reason. It's etch factor. Now, of course, you can make the copper thin and make your etch factor less because you're etching laterally as you're etching down, right?
Mm-hmm.
You can make the copper thinner and do it, but that ends up being a bad transmission line for another reason, because now my copper circuitry is extremely thin and the entire transmission line is thin, right? So much better way to do it is to a pattern plate. And I want to explain this because there's a lot of head trash out there. I don't know if you're familiar with that term, but a lot of head trash out there. So some of our PCB fabricator customers are looking at doing, BGA or chip module packaging substrates, right? And they're trying to do very small features. Let's say the 6 micron range, right?
Okay.
So just for reference, mills 24 microns, right? So they're trying to do that, and a lot of my other customers are like, we don't want any part of that because that's not our expertise. We're not equipped, all that good stuff, right? So
it's got to be hard to get a good yield with that kind of constraint.
The chip guys do it, but on something that's tiny, right? The PCB fabricators are working on 18 by 24 or even larger formats, right? So it's a different world, right? Yeah. And because I've seen semiconductor people come into the industry and say, "Oh, wow, what you're doing is child's play," until they get into a shop,
get away with anything.
Right. Until they get into a shop and actually, dig into the details, and they find out, very different story. Anyway, so every board shop in the United States and really around the world is doing pattern plating, right? In Asia, it's more common to do, print and etch, even on outer layers, but they still do some pattern plating, right? And we do that here, throughout all the US board shops. And that is a semi-additive process. So semi-additive is not a bad word, right? Modified semi-additive is not a bad word. So we're introducing a term called pattern plate 2.0, right? Where because the newer exposure units have that fine line capability already, right? All you need to do is combine a carrier foil, I'll explain about that, and a higher resolution photoresist, right? We talk about photoresist, we talk about aspect ratio. In other words, a ratio of the space you can develop, not the trace you can hold, but the space you can develop versus the thickness, right? So let's say I have a 1.3 mil thick dry film, right? Photoresist, right? If I can develop a 1.3 mil space, that's a 1-to-1 aspect ratio, right? If I can develop a 6 micron space in that same film, that's a it's a 4-to-1 aspect ratio, right? So anyway, or 5-to-1 aspect ratio. So you go with a little bit better film, dry film. You start with a 1.5 or 3 micron foil that's on a 1/2 ounce carrier, so you can handle it, right, and laminate. And then you electroplate, and now you're plating your traces. And light can do things that chemistry can't. The light can go through the resist and give you a straight sidewall. Chemistry, when it etches, it's going to etch laterally as it's etching down, and you have that undercut. And usually it's about half the thickness of the copper. So, if I'm trying to do a 25 micron trace on 1/2 ounce or 18 micron copper, I'm gonna undercut that photoresist to the point where it pops off, and now I've got nothing, right? So plating those fine lines are way easier. But again, we're not trying to do 6 micron substrate stuff. I'm talking like between, let's say, 25 and 50 micron for BGA fan out. That's what we call pattern plate 2.0. The only thing that my customers seem to struggle with that, the few that have adopted this, is the etching, because the etchers, whether it's for inner layers or outer layers, they're made to etch 1/2 ounce, 1 ounce, 2 ounce, 3 ounce copper, right? And now we're trying to etch, 1/16 ounce copper. So really, what they need is a conveyorized micro etch. You can do it in a tank. But when you're trying to get between traces, it's much better to have that solution exchange from a spray system. Conveyorized micro etch. Some people have the spin etchers. I don't know if you've seen them, but where you put a panel in and then the spray bar, will spin and spray on the panel. That's good.
Better surface energy across the whole thing that way, right?
You're right. But I think just a well-run conveyorized spray micro etch, and then that's really been the only hang up in doing this kind of stuff. So it's a big opportunity for the industry to be able to manage the components that we're being told are coming down the road. So
we had that in Hazel, right? Like a little micro etch before we dip the pot, right? So would you even something like that, or is that still too much of a tank to do?
No, you're talking about the micro etch like prior to Hassel?
Yeah. Yep.
Yeah, that's in the right range. Yeah, 1.5. Yeah, so typically those will remove 25 micro inches, and the 1.5 micron copper is 60 micro inches. So you might have to either increase the etch concentration or reduce the speed, but you're in the ballpark.
So probably just like run a coupon, see your weight, right, type of thing.
Yeah, exactly.
Yeah.
Yep.
And then wow, so you guys did all the math for them already. That's the only thing I loved about PCB Fab suppliers is like they would literally hand you a guide specifically for your machines for your process, and they would say, okay, this is how you do the coupon test, right? And they would hold your hand and they would say, okay, we want to see these numbers, right? And then we're going to add this amount of this chemical to it to, balance it out.
Have you ever done backlights or hull cells or anything?
Yeah, of course. Yeah. I kind of miss the hull cell a little bit, to be honest with you, because
What's that for Elias? Obviously, I know what that is, but for Elias, go ahead and explain that.
In my tanks, we only had brightener and carrier, right, and sulfuric. I know they got leveler now, right? That's sounds like a cheat code. I can't stand it, but it's it's the new world. But yeah, so you have these. You can get this thing called burning, right, and your copper becomes brittle, and it's really bad. And you don't want to notice it on a panel, right? You want to notice it in your hull cell. So hopefully you're taking preventative maintenance steps, taking these test coupons, and you'll do this. You'll actually act like you're actually plating a circuit board with the coupon, right? Almost. And sometimes
hull cell. Hull cell is essentially a mini plating tank. Yep. And you angle your work so you mimic different current densities. And as Sean mentioned, you can find out where your burn threshold is in terms of amps. So it's just a great way. It's a great diagnostic tool for your plating, and it's a way to maintain some of the chemistries. We have something called CVS now for measuring, not to be confused with the drugstore, but CVS is used to measure brightener and leveler concentrations, brightener, leveler, carrier. You can do with CVS, but the hull cell is still a pretty powerful tool. Once again, if you become experienced at running this, there's human intuition that's not going to be replaced anytime soon on how to maintain the chemistry. So, in reading a hull cell and saying, yeah, I need a little of this, I need a little of that. So anyway.
Well, that was what I kind of talked about. We had another AI guy on, Sean Patterson, and he was talking about, putting a pH probe in his tank, right? In his plating tank, and having it send the things to him. And I was like, well, I mean, eventually you could get it to the point where if you could have it do titrations or things like that, you could literally just figure out, okay, well then pump this much liquid in this solution into the tank and
maintain it.
Yeah, I mean, I don't know how much I would trust it, right? Because I'm so used to manually everything. But
we do have process controllers now that do analyticals and then make replenishments. They're not AI driven, at least not yet. But the data is cloud based, and you can set for email alerts.
So one of the things we talked about was the CAF, which is obviously the problems on the internal layers. Another thing we learned about, Elias and I at least, right? We learned about the dendritic growth that happens when you have EMC events on the outside layers, right? And HDI bringing components way closer together makes it much more likely for these type of events to occur. So what happens from like a materials level to help kind of prevent those type of events and help keep your circuits protected from dendritic growth?
Well, solder mask is a big benefit for that. That's one of the things that it can do, and it's a liquid, so it seals pretty well. If you're talking about between traces, usually dendritic growth happens in outer layers. That's one of the reasons why for space we don't like immersion silver and immersion tin, because you can have filament growth. But the material also plays a role in it as well. How much does it take on moisture? How smooth is the surface? Is there any surface contaminants? Of course, that's why we do ionic testing, to make sure there isn't, enough of a pathway in what's on the surface. Another important component is, though, the copper foil you etch off. The copper foil has dendritic copper plated on purpose to improve adhesion. And your outer layer adhesion is important because, those copper pads have to support your components. There's it's not just the assembly process, but even in handling, you want to make sure you have enough adhesion on your copper pads that if you brush up against a component, the pad's not going to pop off the surface, right? So there's also bond treatments put onto the backside of that copper foil. Zinc actually has a multiple role. It actually alloys with the copper during lamination. And if you don't clean all that off in the etch process, then you could leave some residues behind that will contribute to that kind of growth. We call them high resistance shorts in electrical test, but and moisture plays a role in that. But yeah, those are things you can do. You can do some cleaning steps, and then of course the solder mask cut will kind of seal everything up, on the outer layer.
I'm looking through my old PCB photos. There's a stack of material, and it came in saran wrapped, and it was a rainy day outside, right? So the guy just kept loading it on there, and look at that right there. So that's how the copper foil should look, right? And that's how it was looking after that. It was just, yeah. So we're gonna have some cleaning to do on that way, I was actually looking for this one that it was like a piece of the PCB that actually peeled up. I was looking at the other day. I was kind of curious to get your opinion on it, but I'm not gonna be able to find it. I have like too many photos of PCB Fab. But
I've heard, I don't know if it's true or not, but that like something like ketchup could actually remove that.
Don't say you heard. I showed him. So there was this job. I can't show that. I can't show the photo. I will talk about it all day long. I can't show the photo of the board because it's too obvious who it is. But trust me, if it wasn't, I would just run it and cross my fingers. But so like we had this board, and just imagine an antenna board. We'll put it that way, right? So basic, no mask, right? And the boards had clearly like fingerprints and just like
the oils from your fingers on them and stuff,
right? And then not all of them had it, so it wasn't like I could just, it's not uniform, and it just, you could just tell they looked terrible. And I didn't have any micro-etch at the shop, so I decided to we threw ketchup at it and let it sit for a little bit, and then we took the soft side. This is very important. The soft side of a Scotch-Brite, and scrubbed away, and then rinsed it off. And am I wrong, dude? When I showed you the before and after, how did that board look?
It's a results-based industry, and the results were pretty gosh darn good.
Yeah, and it worked great. So
you can add salt to ketchup and make it even more effective. That gets some chloride ions in there. That gives you a little bit of a bite. The only challenge with using ketchup, though, is you gotta get it off because it's gonna corrode the copper if you don't leave any of it behind.
It'll keep working, right?
It'll
just keep working.
Yeah.
Yeah, it's not a long based process. It's just,
if I wanted to solder if I'm doing rework on a board and I want to solder onto a pad, pencil eraser is nice because it's dry, so it doesn't leave anything behind, and you just hit it with a little bit of air.
I thought you were going to say, I grabbed me a Heinz 57 and just start going to town.
That's good. Well, Chris, I know, for one, Sean's attention span is pretty short, so we like to kind of stop these before we lose them. So we definitely want to thank you for your time. You've been super generous with it, and we want to give you a chance to go ahead and share more about what you do daily and what Inselectro offers.
Yeah, so we're a material supplier. So we supply all kinds of materials for electronics: conductive inks, Mylar, Kapton, Pyrolex flex circuit materials, EMC and Arlon copper clad laminates, DuPont chemistries, Focus Tech chemistries. We make controllers, make entry and backup. We make copper bonded to aluminum. As I mentioned, we have this new product called Electron Inks that's alternative to sputtering. Really cool technology, disruptive technology. If you want to put a shield layer and circuits in places you never could before in an atmosphere environment, great new process for that. We do drill bits. We do all kinds of things. Basically everything but solder mask we do for PCB and for printed electronics. The printed electronics folks, they supply materials, the silver chloride for doing chemical sensors, that are embedded in things like glucose test strips. That's stuff that we do. So we also were very active in the industry. I like to provide training materials for folks. We just do it. It's not something we charge for. Like I said, I have what is electroless copper, and it's agnostic. It just goes over the technology. Little tidbit: electroless copper came out of a test for diabetes. I don't know if you know that, but that was developed around 1850. That it was discovered that if you had reducing sugars in your blood, if you added copper sulfate, sodium hydroxide, put the test tube over a flame, if the walls plated with copper, you were diabetic. So anyway, that was
in 1850.
Yeah,
that's wild.
Yeah, I think actually technically it was somewhere around 1848, but the 1850s ballpark is close enough. But yeah, so so this is my world. I mean, working on stuff like material science for electronics.
So like we do some thick film stuff. So there's a good chance that you supply like the conductive and dielectric ink and stuff that we use to build up the layers on the ceramic.
Oh yeah, so thick film fired on. Yeah, yeah. We have something called green tape that's flexible, punchable, drillable. But then when you fire it, it turns into rigid ceramic substrate material.
Oh, sweet.
Yeah. So yeah, we've got a lot of different products. So maybe we can help you out. But yeah, this is our world. We've been around since 1964, and Selectro has. I've been around a little bit longer than that. But yeah, we've been around a long time, and this is our business. So hopefully we can help the industry and help people keep this technology in the U.S., keep it alive, keep it innovative, provide good jobs to younger folks who are entering the industry, and yeah, that's what we do.
Yeah, pass it forward, keep it vibrant, and
yeah.
Very cool. Well, I know from all of us here, we learned a ton. It was super enjoyable, and we are very grateful for your time. Thanks to the audience for listening and following along. Make sure to hit the like and subscribe and all that on YouTube or whatever streaming service you use to listen. And hopefully we see you again next time. Thank you.
Yeah. Thank you, guys.
Thanks,
You're quite welcome. And yeah, it's great to be able to talk about this stuff in a forum like this. So
yeah, it was great. Thank you.